Okay, hello and welcome to Equity Education, the chemistry version. And today we're going to be looking at Carbon-13 NMR. And you're going to be doing quite a lot of work and figuring it out yourself. So we better get started. So Carbon-13 NMR. So Carbon-13 NMR tells us the number of different carbon environments. It also tells us the type of carbon environment. This can be found by looking at the chemical shift data. Okay, so a very brief section on how it works. There is another video if you want to go into more in depth into this. So why does it work? So carbon-13 has an uneven number of nucleons. And nucleons are the number of protons and neutrons in the nucleus. So in this example, obviously equals 13. So these can be excited to produce a signal which can help to identify organic structure. As I say, this is really simplified. If you want a more detailed explanation, watch the previous video on spectroscopic techniques. Okay, so what is chemical shift? So chemical shift occurs because nuclei can be shielded by electronegative atoms or groups. The more electronegative an atom or group, the more shielded the carbon nuclei is. This means more energy is needed to excite the nuclei. This means that carbon-13 nuclei in different groups will need different amounts of energy to excite them, and this is called chemical shift. Okay, so I'll just do a very quick diagram here. So if I've got my nuclei in my low state, and this can be my high state. Okay, so I might need a certain amount of energy to promote my nucleon to my higher state. Okay, however, if that nuclei is surrounded by electronegative groups or atoms, it will require more energy to promote my nucleon into the high state. Okay, and this is really what chemical shift is. I don't want to go into that into much more detail, but that's basically what it means. And this means that we get these tables. Now I've taken this from the OCR chemistry syllabus, but you might see different tables dependent on what syllabus you're doing. Yeah, but the values should be very similar. So we can see that the C double bond O, which has oxygen, which is electronegative, and we've got a double bond, so there's a lot of electron density surrounding my carbon nuclei, therefore requires lots more energy to get this carbon nuclei promoted. So it has a large chemical shift value between 220 and 160, whereas if you go all the way down to the right, then we can see CC, which doesn't have any electronegative difference, so it doesn't have a very big chemical shift difference. I don't really want to say any more than that. You just have to be able to use this table to identify the different groups, and I think it will become more apparent as we go through. Okay, so this is important. So carbon-13 NMR only tells us the number and type of carbon environments. it gives no information about the number and type of proton environments. So we have carbon NMR, 13 carbon NMR, and proton NMR as well. There'll be another video about proton NMR as well. Okay, so what constitutes as different carbon environments? So to work this out, we must look at the neighbouring atoms attached to the carbon we are looking at. If they are not mirrored exactly on both sides, then the carbon is in a different environment. E.g., and I want you to have a go at drawing the displayed formula of chloropropane and 2-chloropropane. Okay, so I'm sure everyone has drawn these two. So I have chloropropane or 1-chloropropane and 2-chloropropane. Now if I look at my chloropropane, I have 3 carbon atoms. And there is no symmetry, there's no mirroring going on, so all of these carbon environments are different. So I would have one carbon environment here. Let's change the colour. Another one here and another one here. So you may say that CH2 is the same as the CH2 here, but it's not, because it's attached to this chlorine. It's electronegative chlorine atom at the end, which would change the chemical shift and hence the energy required to promote it into the higher energy state. Okay, over here though, we have something called equivalent carbon atoms. So we can say that A, which is CH3, and my A here, are equivalent. So this carbon and this carbon, whereas the one in the middle is different because it's attached to a Cl and a H. Okay, so this has been mirrored completely, exactly. So what does that mean? Well, that means that we are going to get 3 peaks in our chloropropane spectrum, and we're going to get 2 peaks in our 2-chloropropane spectrum. Now I want you to have a look at where you think these peaks may be, and you may want to have a look at using this. Okay, I would sketch on a piece of paper, see if you can work it out, and I will go through it with you in a minute. Okay, so I've done a very bad drawing, but it's going to have something that looks like this. So we know that chloropropane will have 3 different carbon environments, 3 peaks, because it has 3 different carbon environments, whereas 2-chloropropane will only have 2 peaks because there's only 2 different carbon environments. I can work out that, in general, this is probably going to be my CCl peak, because if I look at the chemical shift value, it's between, what is it, between 50 and 20 for my CCl bond. Okay, which means that this one will also be my CCl bond, and the second peak here is more than likely to be the CH2, and this will be the CH3. Now I've guessed that, and I've said that the peak which is shifted the furthest away is because it's next to the most electronegative element, which is Cl. I know that my 2 A's here, my 2 A's are equivalent carbon groups, therefore I only have 1 peak. Okay, so we would say that the carbons, the CH3 carbons in 2-chloropropane are said to be equivalent. And we could tell which spectrum was which by counting the number of peaks. And there is something important that I would like to say. Our axis are absorbance and parts per million, so this chemical shift down here. but we can't tell. We cannot tell the number of carbons in each environment. We can only tell the different number of carbon environments and the type of carbon environments. Okay, so moving on. I think this will become more self-explanatory as we keep practicing with these. So here's another spectrum I have, and I have 2 peaks. Right. So how many different carbon environments are there? I'm sure you're going to be able to work this out. I'll give you a second. Okay, I'm sure you've managed to work this out. We've got 2 peaks, therefore there must be 2 different carbon environments because we've got 2 peaks. Okay, so the spectrum above is of ethanol. How can we identify which peak signifies which carbon? So I know that the formula for ethanol is CH3 CH2OH. Okay, I'll give you a minute to think about it. You may want to refer to your chemical shift table. Okay, so I'm sure you've figured this out. So if I go back up to my table, I can see that the CO peak has shifted further downfield in values between 90 and 50 parts per million, which must mean that this, the peak that has shifted the furthest down, must be my CO peak. Here's my CO peak, which also must mean that I have my CC peak, which would be my CC peak here. Okay, hope that makes sense. Okay, so we will move on. Okay, so propanone carbon-13 NMR spectrum is shown below. Answer the following questions based on the spectrum. So before we do that, I'd like you to draw the displayed formula of propanone. Okay, now we can have a go at answering the question. So how many different carbon environments are there? Identify the carbons responsible for the peaks on the spectrum. Well, I don't think I need to give you any time. You know that there are 2 different carbon environments because we have 2 peaks. So 2 different carbon environments because of 2 peaks. And just to make it a bit easier, because I think I may have made it a bit confusing using C and CH2, we're going to label these as this CH3 will be 1 carbon environment. Remember, it's mirrored exactly. So these carbons are equivalent, and this will be my 2nd carbon environment. Okay, so identify the carbons responsible for the peaks on the spectrum. Well, now I need to look at my chemical shift. So look at my chemical shift data. And you will find that the C double bond O peak, if I go all the way back up, is going to be shifted way downfield between 220 and 160. So this must be my C2, which is what I have here, and this must be my C1. Okay, right, moving on. So I think I would like you to have a go at doing all of this on your own, so I'll give you 10 minutes to draw out the structure of But3N2O, how many peaks would the following molecule have, and then have a go at drawing the structure, the spectrum for me. Okay, right, so how do we get on? So first of all, you have to be able to draw the structure. So it ends in -one, so we know it's a ketone, but it's also got a double bond on the third carbon. So it's going to look like But3N2O is going to look like this. So how many peaks would the following molecule have? Well, it would have four peaks because it has 4 different carbon environments. It's not symmetrical, so all of these carbon environments are different. So I've labelled them C1, C2, C3, C4. Okay, so from your knowledge of carbon-13 NMR, draw out a fully labelled spectrum for this molecule. So I know there will be 4 peaks, and I can label them as C1, C2, C3, and C4. So if I go back up to my chemical shift values, I know the furthest down field will be my C double bond O. Next will be my 2 carbons in the C double bond C, and all the way down here will be my C bond. Okay, so I can go back down and have a look at this, and I can just make it a bit more obvious. So this will be about 180, and it will be my C double bond O. This will be about 140, and down here will be about 30. Okay, all from looking up my data booklet, my chemical shift values in my data booklet. Okay, so we'll just go back up here. So this is my C2, which is here. This is my carbons in the double bond, C3 and C4. My C3 technically will be the shifted furthest down because it's next to the electronegative oxygen, or it's closer to the C double bond O. Therefore will shift further down because it will have more shielding. Then I will have my C4, and all the way close to the ends, my smallest parts per million would be my C1. Okay, hope this is starting to make sense. You do have to keep practicing this. Okay, and lastly, probably the hardest one, so aromatic C13 NMR. I'll just give you a minute to read through it. Okay, so first of all, I'd like you to draw out the different isomers of dinitrobenzene. Okay, so have a go at drawing out these isomers. Okay, so I'm sure you've worked this out. So here are my different isomers of dinitrobenzene. So I can have 1,2-dinitrobenzene, 1,3-dinitrobenzene, and 1,4-dinitrobenzenes. So now I'd like you to have a go at working out how many different carbon NMR environments there will be for each isomer. Remember, you will have some equivalent carbon environments. Okay, have a go at this. Okay, right, so it is quite tricky and you do need to practice it. But I think I've worked it out. So how many different carbon environments will there be for each isomer? So my first isomer, my A's are going to be equivalent, my B's are going to be equivalent, and my C's are going to be equivalent. Therefore, they're going to be 3 different carbon environments. So this is the same as saying 3 peaks. And our next isomer, we'll have 1, 2, 3, 4 peaks. And our next one, we're only going to have 2 peaks, or 2 different carbon environments. Okay, it is quite tricky. You do need to just go around and try and mirror them up. Right, and lastly, what will be the range of ppm that the peaks will appear in? Okay, well, we will see them in the range between, to go all the way back up to find our aromatic range, so ppm range, which is 160 to 110, because they're all part of this aromatic structure. I can't remember what we said, 160 to 110 ppm, because they are aromatic. Okay, right. I hope that was useful. We will be going on to proton NMR as well. So carbon-13 NMR isn't too bad if you keep practicing. And proton NMR is our next video that we'll be doing on spectroscopic techniques. Okay, hope that was useful, and I will see you next time. Okay, bye-bye.